How's it going, AS Math? Absent students, COLA students, it's your boy, Mr. Knight, back with another fire lesson. Okay, we are going to actually extend our idea of derivatives today because we are not done with calculus. We are only halfway done with calculus. We are actually going to visit the derivatives alternate form, the antiderivative, as some people call it, which is called integration. Okay? Integration has two working definitions that we're going to look at in this class. The second one we'll see later on. The first one, which is way easier to grasp, is just it's reverse differentiation. It's the opposite of a derivative. And so we're going to just work with that, get comfortable with that idea, and work backwards a little bit, okay? So if I give you these three derivatives right here, I want us to try to work backwards and get the original curve. The curve we would have got before we took the derivative. So if I have 3x to the third, let's see. Well, I know normally if I do my power rule, I normally take 1 off. So I'm going to add 1 to my exponent. So I get x to the 4th. All right, and then normally I take that exponent and I move it out front and multiply. So 4 times what is going to give me 3? Turns out be 3/4, right? Well, let's see if I put a 4 in front, multiply that out. Yeah, I end up getting 3x to the third. Sweet. There's reverse differentiation. Okay, let's build off of that. Let's look at this guy right here. 5x squared plus x. Again, I am going to add 1 to my exponent, x to the third. And then 3 times what gives me 5? Again, that has got to be 5/3, which is kind of weird, right? A weird coefficient, but it works out. I put a 3 out in front, multiply, 3's cancel, and I would get 5x squared. And then I just have this plus x. So again, I got to add 1 to my exponent. I get x squared. All right, what times 2 is going to give me just 1? Well, that would be the reciprocal of 2. Just 1/2. And that guy works out. There's the reverse differentiation. And let's do it with this last example. Again, this guy has to be x squared. 2 times what gives me 3? Well, it's got to be 3/2. And then I just have this plus 5x. Actually, I could just tack on the variable, because if I take the derivative of that, I just end up getting my 5. All right, so we kind of, it's kind of weird, right? It's a weird process. And man, working backwards, maybe you found that a little tricky. That's okay. It was really hard for me at first, so let's develop some kind of rule, a new rule for it. But first, well, actually, I think we're jumping right into it. Let's look at that rule for differentiating. Okay, let's recall the power rule for derivatives. If I'm given y equals x to the n, we know that we take this power, we move it out in front, so I get nx, and then I got to take 1 off of my power, so that's nx to the n minus 1 power. And that's how we take the derivative, okay? Again, let's kind of see this with different examples, kind of generalize this. Well, if I have y equals x to the n plus 1, well, I'm going to put that in front, okay? So that'll give me n plus 1. And that'll be x to the, well, I'm subtracting 1 off of this now, so I'm just left with n. Okay? I promise this will be useful, okay? Also, we also know that y equals 1 over n plus 1, x to the n plus 1. We can also do that too. Again, I take my power, my n plus 1, and I'm going to move it in front. Well, I'm going to end up getting n plus 1 over n plus 1, which just cancels out. So I am left with an x, okay? And if I subtract 1 off of this, again, I get x to the n power. So actually, this is really, really critical, these two right here. This is kind of telling us what we need to do. So if I integrated x to the n, right, because I took the derivative of this to get here, just like I would have taken the derivative of this to get to here, okay? So I took the derivative of this to get to here. That means going the other way. If I wanted to integrate this, well, that literally gives me 1 over n plus 1 times x to the n plus 1. And that is my reverse power rule, I guess we could call it. We'll call it reverse power rule for right now. Okay, and this is true for all real values of the power n, except if we raise it to the -1 power. You can try that on your own and go for it and just kind of play around with that idea, but you will be stuck very quickly. So keep that in mind, okay? I did try to play around with it a little bit ago. Cool, we have this, this generalization here. Now, we've been doing the reverse differentiation, but there is a consequence of doing that we need to talk about. And that brings us to general versus particular solutions. Okay, let's break some of this stuff down. So if I give you dy dx equals something, let's say 2x, we call this guy right here a differential equation. That's like the official name of it. Well, when we solve the differential equation for y, because instead of, keeping dy dx, maybe we want to get the original curve back, the y, right, y equals, that itself is what integration really is in terms of this first working definition we have. Okay, so if I did my reverse power rule, I would find that y is equal to x squared, right? Yeah, just x squared, right? Hold that thought for right now. Let's go to Desmos. Okay, so I want to actually look at these three curves, and this is kind of actually out of your book. But if you notice, all of these curves are x to the third power. But notice, they each have a different constant. This one has a constant of 0. If I took the derivative of all of these guys, well, that would give me 3x squared, wouldn't it? Okay. Here's the thing. I don't know what that constant is when I do my integral, right? When I do integration. That's kind of a problem. That means I'm getting y equals x squared plus something or minus something. I don't know what that something is. It could really be anything. Here is where we introduce what we call the arbitrary constant, or just the constant c, okay? Since we can have any constant after this guy, we must include plus c after we do integration. Thus, we refer to this equation, y equals x squared plus c, as the general solution. In general, this is what the integral is, or the solution is to this differential equation. Okay, that's the general solution. We don't know what c is. Okay, a particular solution, well, sometimes is able to be done when you have additional information. That additional information that might be useful is, let's say that the curve y equals x squared plus 3, let's say it passes through a point 2, 1. Well, similar to how we solve for the y-intercept when we have linear equations, well, we could plug this x and y in to our equation here and solve for c. And that's actually what I end up doing. And once I do that, I find that c is actually equal to -3 based off this given information. Thus, y equals x squared minus 3 is the particular solution. When we know what the constant is, that's when we have a particular solution. Okay, so just so you're aware of the difference there, because you might be asked to find the general solution, and you might be asked to find the particular solution, and now you have a better idea of what the difference is between those two. So let's work on some examples. Okay, this is everything you're going to need so far. We have the reverse power rule, and we have general and particular solutions. Let's solve some differential equations. So, for example 1. Given that dy dx is equal to 3x squared plus 4x plus 3, we're tasked with two things. We need to find the general solution of this differential equation, and secondly, we need to find the equation of the curve if it passes through 1, 10, which is pretty much screaming particular solution. So let's do that. Well, if we integrate dy dx and do the reverse power rule, this is what I end up getting. And you can refer, and I encourage you to, especially at first, refer to this rule to see what's going on, right? Well, and let's kind of start with this 3x squared, okay, before I reveal. If I want to get that guy integrated, right, well, let's see. So I have, if I'm integrating 3x to the second power, I know I'm going to end up with x to the third power. And that should be next to 1 over n plus 1, which ended up being, once again, that 3. So we have 3 plus 1 right here. Okay. Or I apologize. This should be a 2. My bad. Okay. And because it was n, right? And we said that n was 2, right? So I'm adding 1 to n to get 3, and I'm taking this 2, and that's kind of where I'm putting it, right, in relation to all this, right? But I also have this 3. I can't forget about that, guys. So instead of a 1 up here, I'll write that as a 3. And so I end up getting 3 over 3, which is 1, which is just x to the 3rd power, would be the integral of this guy. And yeah, you can see if you do the derivative of this, you end up getting 3x squared back. Okay, so I did that for each of these terms because that's how the power rule can work, right? So I ended up getting this guy right here. And you saw that I get x cubed, and I did something similar with each of these guys. Okay, if you need to pause the video and take your time seeing how I'm doing that, please do so. Once you feel more comfortable with that and you get more of the repetition down, integrals won't take you so long to do. They're just going the other way is hard. Okay. We end up though with this general curve equation where c is of course a constant. Now we know that this guy is passing through for part 2 1, 10. So I'm going to plug in for x and y. I'm going to plug in my 1 and my 10 respectively. By the way, this should be y equals, right? So I plug in for y, I plug in my 10, and I plug in for x, my 1. And solving for that, I end up getting c equals 4. Therefore, my equation, my particular solution is y equals this curve right here. Okay? And that's all there is to it. Now, part 2, or example 2, I mean, is going to be very similar to this, although we are going to have to rely on max and mins just a little bit. Okay? So what we looked at actually pretty recently with the optimization. So it's giving us the gradient function of a curve. It's saying dy dx equals 4x minus 12. Okay. Keeping that in mind, we need to do 2 things. Okay. First of all, we're given that the minimum value for y is just 16. Okay, so this guy is probably going to look something like this maybe, or I just know it has a minimum of 16 for y. By considering the gradient function, we need to find the corresponding x value. Part 2 is saying use the gradient function from part 1, part 1's answer to find the equation of the curve. Okay, so part 1 is really saying considering the gradient function, we're going to find the corresponding x value when it gives us this minimum. Since we're talking about minimums or maximums, those are stationary points, and using the derivative to find stationary points, you just set your gradient equal to 0, and you solve for that x value. We end up finding that x equals 3, and that is where our stationary point is. Therefore, the point 3, 16 must exist if y is a corresponding, or 16 is a corresponding y value. So for part 2, knowing that dy dx is equal to 4x minus 12, again, I want to find the equation of the curve. I'd like to find the particular solution. So integrating this guy, I end up getting y equals 2x squared minus 12x plus c. Okay, and like I said, I know that 3, 16 is on this curve. So to find c, I'm going to plug in 3 for x and 16 for y, solve it out for c. I find that c is equal to 34. Therefore, my solution, my particular solution, is 2x squared minus 12x plus 34. This is Mr. Knight. Peace and out. See you later.